Okay guys, so in this lecture we'll be starting off with comparing the rate of reaction with AgNO3. We had discussed in the previous lecture about the reaction of compounds with AgNO3, so we'll be starting off with that only. Okay, so we will be compare rate of reaction with AgNO3. Okay, so here are the examples. We have first second one is, third one is this one. Okay, so what would be the rate of reaction when we'll be reacting this with AgNO3? So when we'll be reacting with this with AgNO3, first of all the formation of carbocations would be there on the carbon which is having iodine attached with it. So now we have to compare the stability of this carbocations. Okay, so in this case this compound is obviously what this compound is we can see the resonance going on in this compound and in this compound, but this compound is non-aromatic and this compound is anti-aromatic. Why? Because it is having 4 pi electrons and it is planar, cyclic, and delocalization is taking place. Hence 2 would be more stable than 1, and in turn 3 would be the least stable. So just a second, I actually did something wrong here. So this is also non-aromatic compound, so 2 would be greater than 3, which in turn would be greater than 1. Okay, let's study for compare for this. This one and this one. Okay, so during the time of reaction all this will go, and in those places carbocation formation would be there. Okay, so what is the stability? This is obviously anti-aromatic, this is aromatic, and this is non-aromatic. So stability order would be 2, 3, 1. Okay, I hope you are following. What is the stability or the rate of reaction with AgNO3? Again we will be removing this, in place positive charge will come, and let us compare the stability of this over this. So obviously this is aromatic, this is non-aromatic, so 1 would be greater than 2. Let's look into this example where we have this one and this one. Obviously this will form an anti-aromatic carbocation, this will form a non-aromatic carbocation. Hence stability of 2 is greater than 1. Same is the rate of reaction with AgNO3. Let's look at this example. We have something like this and something like this. Obviously in this case resonating structures are possible when because of the presence of lone pairs on the oxygen atom, so it will be non-resonance, hence 1 is more stable than 2. No need to think anything more about this. Okay, so let us compare for these two structures. We have something like this and we have something like this. What will happen when it reacts with AgNO3? So when this actually reacts with AgNO3, it will form something like a highly unstable allyl cation. We have discussed it so many times that whenever it is forming as an intermediate, just forget about the reaction. 2 is more stable than 1. Rate of reaction of second compound is more than rate of reaction of first compound. Let us compare between this and this. So in the place of positive sign, in the place of Br, we will have a positive sign. So I hope you are thinking about this, of the formation of vinyl cation. Why? Because alkene would have a positive charge once Br leaves. We don't want that to happen. It is highly unstable, but still more stable than aryl cation. We have discussed it so many times, right? And this would be more stable. Why? Because of resonating structure. Then this, then last this. So let me write down the order: 1 3 2. Let's discuss about this compound. This attached with Br and this attached with Br here. So once Br leaves, we will have a positive charge on this carbon. How many carbons are there? 1 2 3 4 5 6 7 8. So I hope you remember Brett's rule, German scholar Brett's rule, who said that in bicyclo compounds the bridgehead carbon cannot be sp2 hybridized, which will lead to highly unstable ring. Hence 2 is more stable than 1. Okay, let us compare stability between this one and this one. So formation of tertiary carbocation is always favorable. 1 is more stable than 2, or rate of reaction with AgNO3 for the first compound is more favorable than the second compound. Okay, last example. This one and this one and this one. So when iodine leaves this compound, then it would have a positive bond here. So how many number of pi electrons? 1 2 3 4 5 6. It will form aromatic compound. It is cyclic, planar, and delocalization is possible, while in this case delocalization is not possible, because this carbon compound, the carbon atom, will not be involved in any delocalization thing. So it is non-aromatic, and this is a simple carbocation. Carbocation formation would be there. We will just depend on alpha hydrogens. So here we are comparing on the basis of resonating structures, and here we have to go one step down to compare it based on the hyperconjugation, which is at least priority. Hence this would be the most unstable out of these two. So what would be the order? 1 2 3. Okay, so now in the next set of examples, the question is, how will you convert the following compounds into aromatic compounds? How will you convert following compounds into aromatic compounds? Right, so we have something like this. So how will you convert this into aromatic compound? There is a hydrogen attached over here. So aromatic compound will form when this ring will have a positive charge over one of its carbon atoms, right? So this can actually react with H plus. Okay, so I'll just give you the name of reactants which you are allowed to react the organic compound with. You are allowed to react it with H minus, H plus, or Ag plus. Okay, so in this case you can react it with H plus, so that this H can leave as a minus compound and resulting in a positive charge as the cyclopropene atom, carbon atom. Okay, so how will you convert this into aromatic compound? You have hydrogen attached here, so again simple react it with the H plus, so that as you know already that this compound is aromatic, plus H2 would be released. Third is, how will you convert this into aromatic compound? Obviously you know that this is the aromatic, so you can actually react it with Ag plus to conform AgBr. It will settle down as a salt. Okay, how will you react? What will you react with this compound to form aromatic compound? So you know that aromatic compound can be this thing in this structure, right? It can also be this, if you have two negative bonds over here and one it has 6 pi electron, it is having 2 pi electrons, both are having aromatic number of pi electrons. But how will you convert negative charge at this carbon atom? For this to happen, Br must leave as a positive charge atom, which would be highly unstable. So this possibility is out of the way. So this possibility is still there when we react it with Ag plus atom, cation, right? So with this we end this lecture. So in the next lecture we will be seeing some of the exceptions and some more interesting things about aromatic compounds. Okay.